welcome. In part 2 of topic 3, we see this presentation. We take a numerical example to demonstrate the design of an asymptotic observer to estimate a targeted unknown input we call D1 of T by using the most simplified structure. So we propose to have the unknown input D1 of T estimated based on this simplified structure, which we discussed in our previous presentation, part 1. And the functional observer itself is a disturbance decoupled functional observer. It estimates a linear function of the stack vector. We see this reduced order system with unknown inputs. The unknown inputs came from the rest of the unknown inputs. So we like to take an example and to demonstrate how it can be done. We pick an example where we did the decomposition in the previous talk. So we pick matrix IC like before. In here, we have now two unknown inputs. We had two unknown inputs. And so the matrix D has two columns. The first column is D1, which is the one from the last topic. And the other column comes from the other unknown input. Okay, so we got 6 stack variables, 3 output measurements, and 2 unknown input. And the output measurement vector consists of 3 output measurements. All right, so just a remark here, when we look at the matrix C, it is in the canonical form. And because we pick the first output measurement for our decomposition of the unknown input D1 of T. So we have C1, we see the first row of C multiplied by this D1. It's actually a non-zero element. Okay, so it's basically 1 here. And so when we look at this column matrix, we position it to alpha 1 and D1, 2. And so the rest of them, you can easily see it. So you got DR consists of DR1 and DR2. It's just a column. So DR1 is just simply 0 here. So when we look at, when we observe this unknown input matrix and the matrix C, we can see clearly that the requirement where we want the first row of matrix DR to be 0 is happened to be a column. So this element here is just a single 0 element. So it's hold true. So we continue with our decomposition. All right, so we're going to estimate D1 of T in the presence of D2 of T simultaneously affecting the system. And we want to use first derivative. It is possible in this particular example. So we use first derivative of the output measurement number 1. And we design a linear functional observer to estimate a linear function of this system with a unknown input. So let us make the following remark. When we check the observer matching condition, In other words, if someone gives us this matrix C and this matrix D, and if we want to even design a stack observer or do the unknown input according to Howe and Muller, the observer matching condition has to satisfy. Here we got C. When we multiply by D, it's actually doesn't give us a full rank. So this condition does not satisfy. Uh, the matrix D itself has full rank. So this rank is 2. But when we multiply C with D, we only have this submatrix here, and the rank is just 1. So therefore, you can see clearly from the start that existing methods cannot be applied. So let's go ahead with our decomposition techniques. And it works because all we do is we look at this condition. It's actually 0. And the first element in here is actually 1. So look at that. That basically tells us that the unknown input D1 of T is can be completely decoupled from the unknown input D2 of T, and we can use the output measurement number 1 to achieve that. So this is the rest of the decomposition, and then it's actually based on the previous example. So we pick the matrix V, D1 here, important. So that gives us that, and that's the structure of matrix P. With that, it allows us to just select the first derivative of output measurement number 1, and also the rest of the requirements, like this condition holds true if we pick the matrix E according to that. And then when we do the inverse of T times D, have a look at this last row in here. There you go. It's actually, this bit here is 0. So that means that the unknown input D1 is decoupled from D2. And then when we look at this, that bit there, it's actually DR2. Okay, DR2. And so we got this radio order system with an unknown input, where matrix A bar 1, 1, A bar 1, 2, and alpha 1 is 1. So we get this radio order system with an unknown input easily. And then we also obtain the output matrix C tilde 1, and the unknown input D1 is in its simplest form, which contains the first derivative of the output measurement Y1 of T and a linear combination of the stack vector of the reduced order system with disturbance. And the matrix A bar 2, 1 is the same as the one we obtained in the previous example. So let us just also make the following remark. All right, when we look at this matrix C1 tilde, and when we look at this unknown input matrix of the reduced order system, which is that bit there, and then if we take C1 tilde, we multiply by the 2, we get 0 and 0. Whereas the rank of the 2 is 1. However, this condition, the observer matching condition of the reduced order system, does not hold. So even if we say we want to design an observer to estimate the entire stack vector of the reduced order system, we just simply can't do it because this matching condition does not work, we can't just asymptotically estimating x bar 1 of t. You can see that, wow, that is not possible. All right. So, however, on the other hand, it is actually possible for us to design a functional observer to estimate this function here, which is a combination, which is happen to be the last variable, because these two are the outputs, and this is basically the last variable of this vector x bar 1 of t. X bar 1 of t has 5 stack variables. In any case, it is possible to solve for the 3 couple matrix equations for those unknown matrices to satisfy these conditions. And the answer is as given below. So we can actually verify that easily, and we can refer to this reference to work out a procedure for solving for these unknown matrices. Okay, so if we can just simply check whether the disturbance decoupled condition is satisfied or not, which is this condition here, we take the matrix L, which is a row, and we multiply by DR2, which is that one, and it happens to be that it's equal to 0, and that bit there also equal to 0. So it's satisfied. And by the way, we obtain a very simple unknown input observer, which asymptotically estimate the unknown input. By the way, this bit here is not the bar, the head, it's actually the 1. Okay, it's actually the unknown input, the 1 of t. So there was a typo in here. This one is the 1 here. Okay. So the unknown input, the 1 of t, is in terms of the first derivative of the output measurement and this functional observer. This functional observer is first order, functional observer. And it's actually the desired observer is insensitive to D2. All right. And so bear in mind that because the observer matching condition for this radio order system does not hold. In other words, the rank of C tilde 1 times DR2 is actually 0. So we can't use any assisted method to estimate the entire stack vector asymptotically. Whereas when we use a functional observer, it is possible to do so. And so let's show the simulation results. Okay, so what we have in here are the simple codes for simulation of this unknown input observer. Okay, so what we have in here is we enter the matrix A, B, C, D in, and we enter the unknown input, arbitrarily generate the unknown input, and then the unknown input D2 as well, because there are 2 unknown inputs coming into the system. And then so the code for simulation, and then this is the equation of omega, this equation here, -4 and so on. And then We use again the Euler's approximation, numerical approximation, to realize the first derivative of the output measurement y1 of t. And then this is the estimation of the unknown input. And so let's cut and paste these codes into MATLAB. And let it run, and it will give us the results. There you go. So let's have a look at the simulation. So we have here the unknown inputs, d1 of t, which is the solid line here, and the dash red line is the estimation of it. And here, this blue dotted line, it's just another unknown input entering the system. It can be of anything, but we just generate like a RAM type unknown input and a sinusoidal type unknown input for D1. The main thing that we see in here is that the unknown input D1 of T and is estimated unknown asymptotically converging to the true unknown input. So D1 hat of T converts asymptotically to D1 of T. We can also look at the error difference, and it should be 0 as well. Okay, so when we look at this example, we can see how simple the estimation of the unknown input is. We have a system with 2 unknown inputs, and we just want to estimate one unknown input in the presence of the other unknown input. And so in doing so, we also selected the output measurement number 1. And this is possible because the observer matching condition for that particular unknown input, for that particular output, actually satisfy. And then the other bit is the entry or the matrix DR1 in here is actually 0. So with that, we are able to obtain an expression, an analytical expression, which is in the simplest form. And now all we need to do is to design a disturbance decoupled functional observer for this reduce order system with unknown input. Okay, with unknown input. Now, the thing here is we have an advantage over existing method. And that is existing method for this particular example. If we need to estimate the entire stack vector, then we are in trouble because the observer matching condition doesn't work. Whereas if we want to estimate just a linear function of it, it actually works. And so we got a very simple structure for our observer. And we already look at the simulation result. And we can see that it's actually doesn't care, it doesn't matter the other unknown input, it still works. All right, so another very important remark that I like to discuss here is, now when we look at the solution for the matrix L, we obtain in here is actually a single row. And of course, when we look at the node space of L, we actually can have 4 independent columns. In other words, if we take L times the R of 2, which is the matrix, the submatrix of matrix DR. Okay. Now we could have up to 4 columns, independent columns. So we can actually characterize. Those unknown inputs that can enter into the system, and we can still ensure that our observer is insensitive to all of them, All right, so we could have up to 4 unknown inputs as long as the metric DR2 belong to the null space of L. Wow. So here is an example. So let's say if we pick this metric DR to be like this structure. Okay. If we make it arbitrary, but it's actually null space of L, then what we can see here is DR1 is a 0, a row here, which is a 0 matrix, 0 row matrix. And that one there, have a look at that. It has 4 columns, independent column. Rank is 4. So in this situation, there are 4 unknown inputs. And those 4 unknown inputs, they are more than the output measurement. The output measurement available here is only 2, but we could have up to 4 unknown inputs. So if the metric DR2, which is the null space of L, and in that case, the observer that we designed previously still works. So we still have D1 asymptotically estimate, this one asymptotically estimate D1, even in the presence of 4 independent unknown inputs in the system. All right, so here is another simulation example I like to show. Okay, so this is D1 topic 3 part 2 with 5 unknown inputs. All right, so we got the same matrix A, C, and D, and now we arbitrarily generating the other 4 unknown inputs. Is that 4? Yeah, 4 unknown input. 1, 2, 3. The other 4 unknown inputs. And so we call them D2, D3, D4, and D5, and then they enter into the system. So there should be some D5 and so on. And then so let's run the simulation, where in this simulation, the observer that we obtain is for D1. Now it can actually, let's clear this. It can actually insensitive to 4 other unknown inputs. Have a look at that. So have a look at that. So it's just arbitrarily generated the unknown input. Like this one is just a square waveform. This is just like a step. This is just a ramp type input and sinusoidal unknown input. The important thing that we can see in here is that the unknown input D1 of T is actually can be estimated asymptotically by D1 hat of T. Okay, so that's the significance of our result. We can have situation where we don't need to have the observer matching condition holds, particularly when it comes to this radio order system. Because we don't need to estimate the entire stack vector x bar 1 of t. Because our primary purpose is to asymptotically estimate a targeted unknown input using a selected output measurement and its first derivative. And so in that situation, we don't want, or we don't need to estimate the entire stack vector. And therefore we can get away with that requirement, which is the observer matching condition. Okay. And the way to solve for those unknown matrices can be done based on the reference here. And the other bit is in this remark here, we show that, in fact, we could have more unknown inputs enter into the system. And those unknown inputs are more than the available output measurements. But still, the observer still asymptotically track the required targeted unknown input in the presence of so many unknown inputs simultaneously affecting the system. Okay, so that's basically this presentation. And in this presentation, it's based on, again, our book in chapter 3, section 3.23. So thank you very much for watching. And so please join me in the next video. The next video, we see topic 3, part 3, where we will ask the following question. Okay, what to do if this is not true? What is the alternative? And therefore, you will see that we're going to propose a sequential, a systematic procedure for selecting the least number of output differentiators. So that always gives us a way to obtain the most simplified structure. If we cannot have one output differentiator, then we go for 2. And so what is the way to do that? Okay, so that will be then explained in the next few presentations. So thank you very much, and I see you again in the next video. Bye.